Welcome. I am going to share some details on our development of a score-to-likelihood ratio model for facial recognition using authentic criminalistic data. And this is a survey which was performed by me, I am Anna Leda, and also by Isabelle Enlund-Åström and Elizabeth Leitet on behalf of the National Forensic Center in Sweden. Some background first. As you all know, AFR, automatic facial recognition, has been used in many applications for identification and verification purposes for some time now. It is also used routinely by many law enforcement agencies to do searches of video recordings against a mugshot database of known criminals. And though this may lead to law enforcement officers finding a suspect, it is usually not enough to use the matching score from a facial recognition system as evidence in court. And the problem is what I like to refer to as the prejudice of the population. So imagine that you compare a set of 3 unknown images to a reference image. They will all receive slightly different face matching scores. And so you can draw a distribution of how much an individual actually looks like himself. This is represented by the red curve. And in a similar manner, by matching images of people you know are not the same, you can draw a distribution of the general variability within the population, which is the green curve. And as in this case, if the 2 distributions are well separated, you can easily draw a matching threshold. Now, instead imagine what happens if you try to match an image of an unknown person to the system. If it produces a score above the matching threshold, you will naturally assume that you have a match, and it is in fact a picture of the same person. But what if you were wrong? What if the variability within the population was something entirely different and instead it looked maybe something like this? Then you should have interpreted the score as a no match. So what's going on here? Well, maybe you just didn't include clowns when you built your model, very likely. So this does not only tell you that some people just should not pursue a career in crime, but it also tells you how important it is to actually choose your training data well. So this brings me back to the matching scores for our automatic facial recognition. In order for the scores to be usable in court, we can use Bayesian statistics to extract a likelihood ratio, which then represents the probability that 2 people in 2 images are in fact images of the same person, but only in the context of a certain population. So the problem and the question mark has been moved from the use of the scores to the choice of this relevant population. And so, what is a relevant population? Well, the best one we could find was a copy of the National Mugshot Database in Sweden. It contains records of identifying information and images of persons suspect of or convicted of a crime. At the time we obtained the copy, it contained roughly 50,000 records, and about 10,000 records are added to it each year. Some are also removed afterhand, but not as many as are added, so the database is in continuous growth. The quality of the data is highly variable. In some cases, images are missing, in other cases, identities are missing, but overall, it is the largest database we know of that is legally available to us, and yet may represent a valid cross-section of the entire population, which is what we want. So, to construct a model from the mugshot database, we performed an all-to-all match of the entire database and producing almost 2 billion scores. After removing some scores which could not be certainly linked to an identity, we ended up with 4,500 scores from images of the same individual. And we then also randomly selected the same number of scores from image matches among individuals who were not the same. We varied these numbers somewhat during the testing phase, as I will show you later, but this is what we ended up with. And here I have put our testing procedure in a little bit of context. So the testing is represented by the black arrows. And we use the facial recognition to produce scores from the training set, and then use these scores to construct several models to convert scores to likelihood ratios. And by evaluating these models for different conditions, we hope to end up with one or a few or a combination of them, which would be suitable for a certain type of real validation cases. This is represented by the red arrows. And in this paper, we present a suggestion for a step-by-step procedure for this particular testing phase. So here are the models that we used. We had a receiver operating characteristics, convex hull. We had a kernel density estimation, KDE. We had a Gaussian approximation, a skewed Gaussian approximation, and finally a linear logistic regression model. So our testing step number 1 is to examine the sensitivity of the proposed models to variations in the content of the training data. So I told you before that the database gets updated with about 10,000 pictures each year. And the question was, does this mean that we need to update the model each year, or maybe each month in order to keep it up to date? We don't know. So for this purpose, we performed a 10-fold cross-validation of our dataset, which now had a total of 9,000 scores in equal distributions between the same source and the different source. And the graph here shows all the models in one image, so it's a little bit crowded, but the important aspect to notice is that some of the models show a strong variation at high and low scores. An example here is circled in red. And in particular, this is true for the KDE and the skewed Gaussian, whereas other models show virtually no straggling at all. And this is an example here is in green. And this is in particular true for the ROC convex hull and the linear logistic regression model. In our testing step number 2, we want to examine the effect of the size of the entire training set on our models. And to do this, we compute the model accuracy and a learning curve. And for those of you who need a brief repetition of the learning curve, I have attached a schoolbook example here on the left. So a learning curve looks at the accuracy when evaluated against both the test and the training data, while simultaneously increasing the number of samples in the training set. And this is a good way to look at if the model is overfitting. And the idea is that if you have a small training set and construct a model from this and then use the same training set to evaluate the model, you will probably end up with a very, very high accuracy because you've overfitted your model. But if you instead introduce unseen test data to the same model, the accuracy will suddenly drop. But if you then increase the number of samples in the training set, you should slowly get some sort of convergence between the accuracy from the test and the training set. So for our models, and I have drawn 3 of them for space restrictions only, here on the right, we couldn't see such an effect. We only had an increase in accuracy for both the test and the training set. But what we could notice was a very stable accuracy for all of the models from about 5,000 samples and upwards. And last, in the testing step number 3, we wanted to examine the effect of the proportion of the training data. So remember that we had some 2 billion samples to choose from, but only 4,500 were from the same source. So the question is, would it benefit us to include some more scores from the different source samples? And to test this, we kept the same source samples at the same amount and reduced the amount of different source samples in the training set and compared the effect of this, and you can see this on the right, to the previously calculated effect of changing the size of the entire data set, which you can see on the left. What we can see here is that the effect of the former is several orders of magnitude larger than that of the latter. And what we're looking at in these curves is actually only the linear logistic regression model. And we have done it. What we've done is to vary the size of the training set as the line grows darker and darker. And what we would like to see is that the lines are approximately in the same place, or as much as possible. So What is not so apparent from either of the graphs is that there is actually a very strong convergence between the last few calculations from approximately 5,000 samples and up, where the lines virtually overlap. So we conclude from this that a symmetric sample size of a few thousand samples should be sufficient for a reasonably stable model. Finally, I just show some results from some of the models. I've chosen 2 here because of space restrictions again. This is the skewed Gaussian and the linear logistic regression model, and you can look up the other ones yourself in the paper. Again, what I want to point out is that for the ECE plot, our curve is actually down very, very low, close to the x-axis, and it's even a bit hard to spot it on this scale. We also wanted to get some numbers out, and so we calculated some accuracy, sensitivity, and specificity for the 5 models. And when doing this, we have actually created an overlap with using an LR grade scale, so that all the LR values between 1/6 and 6 are considered as indeterminate, which means that they are counted as false. And the reason for this is that we wanted to get some dynamic in the analysis. Because it turns out that if we had a fixed threshold of, let's say, LR equals 1, then we got accuracy numbers very, very close to 100% for several models, and this is not too good when we want to compare them. So these are the results, and as you can see, we have also included the CLLR for all of the models here. Finally, here are the finished models that we came up with. We have the ROC convex hull, the skewed Gaussian to the right, linear logistic regression model, which is the flattest straight curve. We have the KDE, and we have a Gaussian. And what is interesting for this graph is to notice that several of the models actually cross the LR equals 1 threshold very, very close to each other, and that they all also are monotically increasing. So some conclusions from this is this is actually the first attempt we have seen to construct and evaluate a score to likelihood ratio model using a national mugshot database. So we would really love some feedback on both the analytical approach and the choice of training data. Is this actually representative of the population, or are there any other options? The goal of this survey was to create a support tool for a manual facial recognition procedure. And to do this, we have then evaluated 5 mathematical models and reached a near 100% discrimination for high-quality images, at least. We do expect that we would need to retrain the model every time the automatic facial recognition algorithm changes. But as far as we can see, we can get away with very, very few model retrainings between database changes. As you remember, we had a very stable model from about 5,000 samples and upwards. And the database only grows with a few thousand samples each year. So that was all for me, and now I open up for question and comments. Thank you.